Welcome DKWP 小工 aboard. Your learning journey starts now. Ever felt like information is just, well, information? And energy is just energy? Like oil and water, right? Wrong. Deep down, they're practically soulmates. Physics talks about energy conservation, info science about bits and bytes. But zoom out, and you see them tangled together in thermodynamics, computation, even life itself. This report? It's your secret decoder ring for this relationship, using something called the DIKWP model. So, how do we untangle this mess? Meet DIKWP. Think of it as a superhero team with 5 members: data, information, knowledge, wisdom, and purpose. D is the raw stuff: numbers, sensor readings, pure data. I is when we find patterns. Oh, look, a temperature trend. K is the big picture, the laws, the why, like energy conservation. W is making smart calls based on that knowledge. And P? That's the North Star, the goal, the why bother. This isn't just a list, it's a dynamic loop where each layer feeds the next, and purpose keeps it all on track. It gives us a common language to talk about both information and energy. No more confusion. Now, let's get nerdy. Remember entropy. Sounds boring, but it's the VIP pass connecting information and energy. Shannon gave us information entropy. H equals minus the sum of P sub I times log base 2 of P sub I, measuring uncertainty in bits. Gibbs did the same for thermodynamic entropy. S equals minus K sub B times the sum of P sub I times natural logarithm of P sub I, in joules per Kelvin. Look familiar? They're twins. Landauer's principle then slams the door shut. Erasing one bit of information costs energy, specifically K sub B times T times natural logarithm of 2. Maxwell's demon thought experiment showed you could use information to seemingly pull energy out of thin air. So, information isn't just fluffy data. It's got physical weight, it's fuel. Okay, so how does this actually work in the real world? Imagine your thermostat. It's a perfect little example of information taming energy. Sensors collect raw data, D, the current temperature. The controller compares it to the target, 22 degrees Celsius. That's information, I. It uses its built-in knowledge, K, like a PID algorithm, to decide how much heat to pump. The heater kicks in, manipulating the energy field. Then, the room warms up, new data comes in, and the cycle repeats. This is a closed loop. Information drives energy, which feeds back to refine information, all guided by purpose, staying comfy while saving juice. DIKWP makes this elegant feedback loop crystal clear. And here's the cool part. We can teach AI to think this way. Using a DIKWP prompt template basically tells the AI, okay, break this down for me, step by step. Let's say we want to cut energy use in AI models. We ask the model to respond using DIKWP. It'll start with raw data, D, maybe energy stats from training runs. Then it'll identify patterns, I, like peak usage times. It'll apply knowledge, K, about efficient algorithms or hardware. It'll propose smart strategies, W, perhaps a mix of pruning and better scheduling. Finally, it'll state the goal, P, like reducing costs by 20%. Suddenly, the AI's answer is structured, comprehensive, and actionable. It's like giving the AI a cheat sheet for brilliant thinking.